Thanks for joining us. I'm coming from a company called ATP, and we have a pretty close partnership with Micron. I think most of our products are based on Micron flash technology. They have been a partner since decades, I would guess. I'm with ATP for just a couple of years, not too long, but my boss is standing there. I have to tell you, there is no time to be too long at ATP. It's a very enjoyable company, as some of the guys know here. However, I would highlight, I think the topic today is thermal solutions. There are some challenges that embedded customers need special solutions for, which we approached. And that's, I think, the basic point of my presentation today. So what we did to serve these special markets. So before I get started, I would spend some words on the partnership we have at Micron. Of course, we are a customer. We use their products, we use Micron flash memory, but the partnership goes beyond just being a buyer of Micron technology. Micron is a pretty well-known vendor, I think, in this space. ATP is a smaller, so we are concentrating on niche markets, whereas customers have very special demands, one of it being thermal solutions. Our relationship so far, beyond buying Micron flash, is that we produce some products that Micron has no large interest to do themselves. It's of course niche products, and they sell as Micron products. It's one part of our partnership. The other one is we have since this year a long time agreement. So we have, if customers ask us where will prices go, we can give them an outlook because we have a pricing and supply agreement done for several years. And of course, Micron shares all their information, means we don't know what they will sell next month, but we have a long-term outlook of where their technology goes, what it will be, and what products we can do from it, which gives us the basis to do our work to our customers who are all thinking in long lifecycle products. So usually when ATP brings products to market, we think about a lifespan of minimum 4 years, 4 to 5 years. And we can only do that with partners as Micron, who give us an outlook how long they will maintain products. Micron, of course, has a bigger customer base and is always top-notch technology. They have a big volume in actual technology. Our customers are also asking for demanding things, means actual technology, but they want to have these products for 4 to 5 years, or sometimes 10 or 15. Depends a bit on the market. I think typical applications would be medical computing, where certifications of devices are very expensive, or transportation, where they rather ask for 15, 20 years the same product. That's certainly something we can't do too. We have to migrate in between, but it's a difference whether you have to migrate like 5 times over 15 years or just 2 times. And that's why they like us, because we are very consistent in delivering the same solutions. We have a lot of customizing we can do to the product. That's not only over-provisioning, it's very special things like anti-sulfur. We can code things for transportation or military. We do extreme tests on our products. I think in defense you often have shock, like 20G testings, and where you might have to redesign products because they simply break over time. That's why we concentrate on those niche markets, because we design everything ourselves and we have control over almost everything in the product. Why we can deliver 4 to 5 years? First of all, Micron has a strategy of maintaining legacy technologies. But as time goes by, I think customers are always asking for bigger capacities for less money. That's the nature of the business. At a certain point in time, lower capacities are not of big interest anymore. And Micron might have no interest in producing the ICs with this flash technology. So we know what's coming up and how long it will be available. That's the info that we share with Micron. And then the second most important is that we buy wafers. Not all of our products are built from self-packed ICs, but a lot of are, especially if they are longer in life cycle. So it might be that we buy ICs from Micron in the beginning, and at some point Micron won't produce them anymore and we start packing them ourselves. Some products are so special we pack them from day one. But since wafers are longer available than the ICs for the reasons I just explained, that gives us the additional 1 or 2 years or even more to have the same product for the customers that they want qualified. The rest is, other music. It's not that unique. I think a lot of our competitors are doing pretty much the same. But since we build our own ICs, we have control of every cell in their flash and not just scan the user space that they may occupy in their products. High temperature. So we call it beat the heat. We had discovered some fields where people have a demand for a high bandwidth SSD while they know it's getting really hot. This is mainly, or the first finding where we had it is automotive testing. So if you have prototypes of cars, we are based in Munich, and we are used to this prototype cars who are mostly covered by some weird patterns. BMW has 6,000 cars on the road who are doing just test driving, and they have the trunk full of technology. They lock everything, front radar, cameras, buses inside, and this is a significant amount of data they write, and they need large capacity SSDs, and they know it's going to be hot, because if you open the trunk, it's just technology. It's not one data logger, it's like 15 of them, and they need SSDs that still give a certain bandwidth, a high bandwidth, at like 70 degrees ambient, which then translates into, 80, 85, sometimes 90 degrees inside the PC. There are CPUs that generate heat, the SSDs, the DRAM, everything produces heat, and they don't bring the air conditioning into the trunk, so they know it's going to be a challenge, and still have to, if you take those automotive data loggers, and it's not the only one who has these kind of requests, they sell the systems with a guaranteed bandwidth in a certain temperature range. So usually the temperature range is minus something, 20 or 40, up to 60 degrees ambient. But inside, you know that a controller at that temperature is easily being above 100 degrees. And that's a challenge, in fact. So other industries who are asking for that is defense, obviously, or aviation, where missions are recorded, stuff like that. Predictive maintenance, if they record like railroads and they have, or a sonar in pipeline inspections where the robot is in a hot liquid and they know the system is already hot because they are in hot oil in a pipeline, then they know it's going to be a challenge to guarantee that bandwidth. So what we then usually do is not, here it is, try it out. This might work for your use case. So we really have a discussion with them, like what does your solution look like? Means what do you do to get rid of the heat? So one approach is, of course, airflow. It's always possible. Most of them have like drive containers because they want to exchange the media. The media then having 2, 4, up to 16 drives in our customer base. Because they want to take a ride, 8 hours, exchange the media, and go back in again and drive again, and then analyze the data in the lab, rather than pulling it off while the system is still in the car. So these are specialized, most aluminum drive containers, and they need a 3D model, for example, of the SSD before they can start building those solutions. They have a rough idea of the temperatures, how much temperature delta there is between a controller and the casing of the IT inside their car or plane or whatever it is. And that's where we start, like getting the idea of what is your bandwidth demand and what's your technical solution. So we, over the last 2-3 years, we worked on methods to predict, like we have that solution and this should do the job in your specific solution. A regular iTemp SSD, so if people come to us and ask for an SSD, a regular one, they say, yeah, I know my system is going to expose to negative temperatures, so I need an iTemp. And they often they assume that if the range is minus 40 to 85, it has a constant performance which most SSDs on the market don't have. So iTemp doesn't mean that up to 85 degrees it works at full performance, it just works. So this is a kind of worst case scenario. It's actually a measurement a customer did on a bad solution, where you can see if the temperature goes up, this is read, this is write, the performance goes down. It goes down in steps, like there are thresholds. If threshold A is met, the controller runs at half the speed, and this way the SSD tries to save its life, not to overheat. With the existing cooling solution, the hope is that the SSD then cools down by lowering the performance. And if it gets going very extreme, like here above 86 degrees, it almost goes to 0. Above that, it would even switch off. So it would tell the system, I don't take any data anymore, I'm gonna reset more or less. And that's exactly what data loggers can't use, right? They are in this range of temperatures and they still want to see significant performance. So we changed the game. The heat is, well, we have various, I think, approaches to it. So first of all, we offer our SSDs with cooling solutions on it. One of it being copper foil, that's really a thin foil covering all ICs, and including the controller, to just have a bigger surface. So from our experience, the controller is the hottest part on an SSD. A controller is, in fact, is an ARM-based 2-core, now with NVMe or PCI Gen 4, it's even 4 cores, and they have in the range of 6 to 8 watts, and that generates heat. That's simply technology. So this is the hottest part. The flash is also getting warm, and the copper foil helps to get a bigger surface to dissipate the warmth on that SSD. If it's going more extreme and if the system has enough space, we offer a 4mm or 8mm solution too, and it goes around the SSD. For the reason with high capacities, you also have ICs on the downside of an SSD, and a cooling that's just applied to the top of an M.2 wouldn't take the heat from the ICs on the downside or beneath the SSD. That's why it's clamped around it and makes that even a bigger surface. Of course, in this case, we also provide 3D models, so a lot of customers then print a 3D model of the SSD and try it out in their system, because embedded systems are, well, not unlike servers, they don't have endless space. And they appreciate we have these models so they can physically check if that's a good fit or not. It adds a 0.3 millimeters on the side, and the downside you're never sure if there are any components on the PCB. That's one approach, that's a simple approach, and it helps already to bring down the temperature by a few degrees, in a range of 2 to 8 degrees in a hot environment. The very smarter approach is that we change the way the SSD reacts to temperatures. So it's not going, oh, I'm hot, I'm going half the speed, but it does it dynamically. So this is a very long period. If you see that in seconds, it's several days, in fact. 16,800 seconds, several hours. Okay, 3,600 is 1 hour. This is an M.2, 4 terabyte. We have that on the booth. We just redesigned it for actual technology, Micron again. And we have a dynamic regulation of how the SSD handles its performance. So it starts high, not at 3 gigabyte like gaming SSDs, because that's not a requirement from our customers. They're more thinking about the 700, 650, 800 megabyte per second. That's mostly their target because they do RAID systems. And as soon as it gets hot, it tries to find the sweet spot on where to operate. So this is an actual solution, an M.2. And you see there are more impacts. So this is when the drive is full, it gets erased and it has to reorganize blocks and pages. So this is called garbage collection, more or less. And the garbage collection before we started this was more significant. It happened more often, and the performance impact was more significant. So these are several thousand seconds, so this garbage collection is not done within milliseconds. It can keep SSD busy for a long period, 300 seconds, 5 minutes. You can't accept data logging not to record at full speed for 5 minutes. Then you would have to put in massive dynamic RAM into a system so it can buffer the data and then write it back as soon as the SSD is ready. So we spread the period so this is longer than normal, but therefore it doesn't go that deep. So we stay above the threshold that our customer wanted. This was our first approach, but it happened very often, and that wasn't usable. And most consumer SSDs, so a lot of our customers come back to us after they did some bad experience with other solutions. And these are the points we worked on, like having a constant performance, can tell them at which temperature we have which performance, and avoid these pitfalls of other things that an SSD does in between. We also did it for UDA2, that we look a bit better. because the U.2, of course, has a bigger surface. You have more ICs in there. The heat spreads easier. And there we achieved like a gigabyte per second, which is beyond the specifications that our customers even demanded. And we are now in the process to come up with B47 technology by the end of the year, where we expect this to be even 50% higher, because we started from scratch and learned our doings. But to be fair, that's already my message for today. So what we do for our customers. I hope I made clear what we have been working on and what we have in portfolio and where our partnership sits. So thank you for having me here.